So here is synchronous machine. So I'm going to first give you introduction on synchronous machine, which is salient pole synchronous machine. So first of all, you know there are two types of synchronous machine. One is synchronous machine. There are two types of synchronous machine. One is cylindrical and another is salient pole synchronous machine. So I'm going to first give you introduction on salient pole synchronous machine because it's little bit difficult than synchronous cylindrical synchronous machine. So let's see. You can see from here there is non-uniform air gap. Here air gap is minimum. Here is also minimum, but here air gap is maximum. Here also maximum air gap. So from here we can say that air gap is non-uniform. So, and one thing, just note it that maximum here is minimum air gap. Okay, so if we go from here to here, air gap will increase. Similarly here also, here will be minimum air gap and here is maximum air gap. So in synchronous machine, this is the direct axis of pole. This is main pole and this is stator. Okay, this is stator, and in stator there are stator winding like that. What actually in synchronous machine, armature winding is placed in stator and field winding placed in rotor side, and we excite the field winding with DC source. Okay, just different from, as you know, in induction machine is just self rotating machine. We don't have to excite it different way. So here we have to excite it different way, means you have to excite by DC source, and in case of induction machine we don't need to excite by separate source. Okay, so why we are exciting with DC voltage source? Just because of we know we have to make the machine to run with synchronous speed. In case of induction machine, we have seen that NR is, which is rotor speed, 1 minus S is Ns, where Ns is synchronous speed and the rotor speed is 1 minus S into Ns, where S is slip, where Ns is just nothing but 120 F by P. When we will study on induction machine, then we'll study on these topics in I'll explain each and everything on these things, like why just came 1 minus S into Ns, etc, etc. Okay, so now just remember that thing, just nr is equal to 1 minus s into ns. So how can we make the machine to run in synchronous speed? Just see, if we can make the sleep 0, then only it is possible to make the run machine in synchronous speed. So let's see. So nr will be ns when s is 0. And you know, in induction machine, fr, which is rotor EMF frequency, which is equal to s into f, where f is line frequency of stator or armature and fr is rotor EMF frequency. So when s is 0, fr is 0. So in case of synchronous machine, fr is nothing but field EMF frequency. For DC source, only f is 0. So for DC source, f is 0. So then only we can make it as 0. fr will be 0 if we use a DC source in the field winding. Okay, is it fine? So it is only possible when we use the DC voltage source in place of field winding. So let's see the working principle or the two reaction theorem of synchronous machine. So as I have already told you that this is direct axis, and this is quadrature axis. So one thing the students just make mistake, which is they think that quadrature axis, direct axis and quadrature axis just the phase difference between quadrature and the direct axis and quadrature axis just 90 degree. But remember, this is not only 90 degree, this is 90 degree electrical, not mechanical. So here I think we don't have to face any problem because it is two pole synchronous machine. Because two pole machine, theta, you know, theta electrical is P by 2 theta mechanical. So for two pole machine, what will happen? Theta electrical is equal to 2 by 2 theta mechanical. So just 2 to cancel out and we'll get theta electrical is equal to theta mechanical. It's okay, there is no problem. But for case of 4 pole or 6 pole, 8 pole machines, you will face some problem if you don't know the actual concept. So let's see. In case of 4 pole machine, suppose here is one pole and here is another pole. There are 4 poles. Okay. So this is the rotor. Okay. So for 4 pole, this is the direct axis and quadrature axis will be, let's see, 90 degree. And one thing you have to know, the adjacent pole, between adjacent pole there is 180 degree electrical phase shift between adjacent two pole. So 90 degree, where will be 90 degree? 90 degree will be just middle of two pole. Okay, if this is your quadrature axis, that will be your if this is direct axis, then that will be your quadrature axis. Just quadrature axis lags the direct axis by 90 degree electrical. Remember it. It's very important. Sometimes you may commit mistake. Okay, so let's see. Here current is flowing from here in that direction. So by right hand rule we can determine the direction of flux. Just because of DC current we have applied here DC voltage V. Okay, so current will flow that direction and flux will flow. Just right hand rule, just think about right hand rule, then you will get the direction of flux. So flux will flow in that direction, upward direction, and just go in that direction. Here also that direction to that direction. Okay, so we know in magnet inner side flux is flowing from south pole to north pole, and in outward direction in pole to or north pole to south pole. Okay, so from if you have studied transformer chapter, then you can understand that the phasor diagram of transformer, here V is applied voltage and flux is, this is main flux, core flux, and this is induced EMF E. So main flux, the induced EMF lags the main flux by 90 degree. Is it fine? So from here we can say that flux, main flux, the angle between main flux and induced EMF will be minus 90 degree, or you can say induced EMF lags the main flux, that is main flux by 90 degree. So let's draw phasor diagram of synchronous salient pole synchronous machine. Phasor diagram. Phasor diagram. So I'm considering that synchronous machine is supplying the load with lagging power factor. So my current will be like that. IA will be IA, that is phasor IA at an angle minus phi. I'm assuming that induction machine. Okay, let's take first induction machine as a alternator. Alternator is nothing but synchronous generator for alternator. Okay, so alternator is supplying the current or load in lagging power factor, cos phi lagging power factor. Phi is angle, so cos phi will be my power factor or alternator power factor. So let's see. Here V is reference. Sorry. So let's draw the phasor diagram of alternator, and we are assuming that alternator supplying the load in lagging power factor, which is I is -5. So I'm assuming that E is induced EMF, and remember the IQ, quadrature axis current, always in phase with induced EMF. And for if as I have taken current as lagging in nature, so ID will be like that, ID. So IA will be like that, IA. So current is lagging in nature, so voltage, obviously voltage will be like that, voltage, and this that will be phi. So if I draw phasor diagram, then here is ID. For direct axis reactance, the voltage drop for direct axis reactance, that will be like that, ID JXD. And for quadrature axis reactance, the voltage drop will be like that, so that will be JIQ JXQIQ, that is V. So angle between induced EMF and the terminal voltage del. So from here you can write it as E phasor, induced voltage phasor for alternator, is E at an angle del. So always remember, for generator or for alternator, del is always positive, but in case of synchronous motor, the load angle, which is del, will be always negative. That is the one of the difference between synchronous motor and synchronous generator or alternator. And from here you can say the angle between induced EMF and current IA is, so let's denote as psi. The angle between, psi is angle between induced EMF and load current, so that is psi. Psi is nothing but phi plus del. Is it fine? So from here you can say, or you can determine the value of ID if you know the value of IA, means load current, actual load current, which will be IA. Suppose ID will be IA sine of psi. Is it okay? Similarly, if you observe here, IQ will be IA cos of psi. And what will be the value of induced EMF? You know the value of applied voltage or the terminal voltage. you know id, xd, xq, iq, but you don't know what is the value of induced emf of alternator. So you have to calculate it. So how can you calculate it? So let's see. See, from here you can see this is nothing but this is V. The angle between V and E is del. So this length is just V cos del, because the angle between E and V is del. So this length is V cos del, and this length is just xd id. This length is xd id. So this is xd id. So from here we can write it as induced EMF E is V cos del plus id xd. Remember, it is just magnitude value of induced EMF. And if you observe from here, then you can get the value of del by just tan del will be ia xq by v plus ia xq cos of phi by v plus ia xq sin of phi. You have to remember this formula if you want to solve problem within very less time. You have to remember. This is very easy to remember, and you have to remember just one formula, then you can remember other formula also for motors, synchronous motors and synchronous generators for leading power factor and synchronous motor lagging power factor, etc, etc. So you have to remember just one formula, and remember this formula is valid only when the armature resistance is neglected. Armature resistance is 0. Otherwise it is not valid. If and only when R is 0, we can solve the problem by using this formula or this phasor diagram. Is it fine? Remember, when armature resistance will be considered, then you have to solve the problems in another way. We have to take the resistance. Here some resistance will come, okay, not only reactance, there will be also some resistance, but generally resistance of synchronous machine are very small. That's why we just neglect it, and in most of the exam they just neglect it. Armature resistance just taken as 0. Armature resistance is 0. So let's see what will happen if we draw the phasor diagram for leading power factor. We have drawn this just for lagging power factor of alternator. Remember, we are studying just alternator, not motor. This is all about alternator when it is working at lagging power factor. So let's see what happens when alternator delivering the power in leading power factor.